The next topic of the lecture is the concept of even and odd functions. These two features of a function that any function could be even, could be odd, or neither of them. Okay, it's not that they have to be one of them. These two features will really simplify the way that we compute the Fourier coefficients of the function f. So that's why it's important to introduce them, and each time we find a function that is even or odd, we can use this information to simplify the computation of the Fourier series coefficient. Of the Fourier coefficients of the function f. So a function f is even if we have this identity for every x. F of minus x is exactly f of x. And a function f is odd if we have f of minus x equal to minus outside the fx for every x. Okay, let's try to maybe illustrate this concept with some examples. The function cosine of x is even. Why? Because we know that cosine of minus x is exactly cosine of x for every x, and we have this graph that we only did between minus pi over 2 and pi over 2, but we can, you can extend the graph if you want. You know that it's a periodic function, so it just repeats itself in outside this interval. Okay, so you can also notice that this piece of graph is quite similar of this piece of graph. And this quite similar thing is just a symmetry with respect to this y-axis. Okay, just to mention that, so this function cosine is even. The function x squared, we know that if we put the minus here, the square doesn't care and just give a positive answer anyway. And in particular, we have that minus x squared is equal to x squared, so the function f is even. And we have again this graph, which is, if we only look at this piece of the graph, this piece is symmetric to this other piece of the graph. And this symmetric idea is with respect to this y-axis. One more example. Fx equal to the modulo of x. Again, minus x, and x has the same distance from 0. So this function is even again. And one more time, we have this piece of the graph symmetric to this piece of the graph with respect to this y-axis. So here we have just this remark. The graph of an even function is symmetric with respect to this y-axis. Okay, enough even functions. Let's take a look to some odd functions. So here we have sine of x. We know that sine of minus x kind of put this minus outside. So we have this identity. Sine of minus x is minus sine of x for every x. Then the function sine is odd. And here we have this piece of the graph that we can compare with this piece of the graph. And we also have some symmetry here, but with respect to the x-axis. Okay. More examples. The function just x minus x is exactly minus 1 times x, so it's an odd function. And again, this piece of the graph is symmetric with respect to this piece of the graph with respect to the x-axis. Okay, one more example. X to the power 3. Okay, so minus x to the power 3. Remember that minus 1 to the power 3 is still minus 1. So we get this, and we verify the definition of being an odd function. And again, this piece of graph with this piece of graph are symmetric with respect to the x-axis. So we have the graph of an odd function is symmetric with respect to this x-axis. Okay. So some basic properties of these odd and even functions related to the integration that they will quite useful to simplify the computation of Fourier coefficients. So basic properties. If f is even, then the integral between minus p and p of f is exactly 2 times the integral from 0 to p of x. So if we go to the examples, we can see that this is related to the this symmetry that we have here. So this guy is symmetric to this other guy, so integrated in the whole interval is the same of integrated twice in half of the interval, and that's what the first property says. Same for here. Integrated in the whole interval is the same as integrated in half of the interval because of this symmetric property. So here again, if we want to integrate in the whole interval, it's the same to integrate twice in one piece of the interval because of this symmetric property. Okay, so that's the first property here when we have even functions. What happens when we have an odd function? The integral of f between minus p and p is exactly 0, and that has to do with the symmetric property with respect to this x-axis. This guy is exactly minus this guy, let's say. So when we compute the integral in the whole interval minus 1, 1 here, we get a 0. And this is exactly what happens here. So I didn't put values here of the interval, but if we pick that interval, we get again a 0 because this guy is minus this guy in some sense. And again here, so for odd functions, when we compute the integral from minus pp, we get a 0. Okay, and we have some properties when we consider product of even and odd functions. So the following product properties can be used to simplify finding the Fourier coefficients of even and odd functions. So what we have here is, okay, if I have two even functions and I multiply them, then I got an even. If I have even odd times odd, I get an odd function. Odd times odd, I get an even function. So you can also think about, let's say, that even is a friend and odd is an enemy. So we can say the friend of my friend is my friend. Then we can say the enemy of my friend is my enemy. And then the enemy of my enemy is my friend. If you want to remember the property, otherwise you just make the computation and see that this is true, like just from the mathematical point of view. Okay. So, how can we use these properties to simplify finding the Fourier coefficients of even and odd functions? Okay. So, assume f is even and of course 2 periodic, because we need this periodicity property to have a Fourier series representation. So in this case, we know that we have this representation. A0, In, the cosine here, Bn, the sine here, with this n and this series. Okay. And we know for Euler's formula that we can compute the coefficients in this way. A0 is f of, this is incomplete. Just 1 second. So dx here. Okay, so A0 has this form, An has this form, f times cosine and f times sine for the Bm. And now here we have the products, right? We can use the first property to compute A0, and these product rules, let's say, to compute, to have information or to simplify An and Bn. We have that f is an even function, so we will know that this guy is exactly 2 times the integral from 0 to p of f, because I'm working with an even function. And here we have even function times even function, because cosine is even, so this product is even, and we can use again this property of, instead of integrating from minus p to p, we can change this to 2 times from 0 to p. And then we have this third, the other property, f is even, sine is odd, so this guy, the product, is odd. Okay, we can say again, the enemy of my friend is my enemy. So this is a 0, because we have the integral from minus p to p of an odd function. And then we use this first property. So remember, just take a quick look to the properties we have. When we have an even function, we can change this integral for 2 times from 0 to p. And then when we have an odd function, the integral from minus p to p is 0. So, and then we have these product rules. So going back to our example, let's say, so if we are working with an f that is even and 2 periodic, and we have its Fourier series representation, we know by the Euler's formula that we can compute the Fourier coefficients in this way. But now we are going to use all these new properties to simplify the computation. So A0, we know this identity because it's the Euler's formula. But now we know that f is even, so we know this other property. And that's why we can put these two here from 0, the integral from 0 to p. So finally we get this orange expression, 1 over p, the integral from 0 to p of x of f. Okay, then an. This identity is just that we are using the Euler's formula, and now we are using the new information. F is even, cosine is even, so the product of these two guys is even. And again, from the new property, we can replace this integral by 2 times from the integral from 0 to p of the same guy. And that's why we get this orange expression. And finally, here we are using Euler's formula and then the new information. F is even, sine is odd, so the product is an odd function. And now we know that for any odd function, the integral between minus p and p is 0, and that's why we have this 0. So, in conclusion, here we have the property. In conclusion, we have, if f is 2 periodic and even, then its Fourier series representation is given by only A0, this expression A0 and this series of an cosine of n pi over px. So there is no bn and sine term. And this is because our function is even. And we also have a new expression for a new formula to compute a0 and an, which are written here. 1 over p from 0, the integral from 0 to p of f, and 2 over p, the integral from 0 to p of f times the cosine function. Okay, so, and this is how we use this new concept of even and odd functions to simplify the computation of Fourier series representation, or let's say the coefficients of the Fourier series representation. Okay, what happens if we have an odd function? Maybe you can already imagine what will happen, but let's take a look. So we have f, an odd function, and two periodic. So we know that we have a series representation, a Fourier series representation for this function f. Okay, so we have again a0, an, cosine, bn, sine. So we have this expression, and we know for Euler's formula how to compute a0. So here, oops, oh, so here we are using Euler's formula, which is exactly that, but now we use the new information that we just saw. If we have an odd function integrated in this interval from minus pp, we know that this is exactly 0. Then, an, here we're using Euler's formula, and then the next step is using the new information. We have an odd function, we know that cosine is even, so we have that the product is an odd function, and we are still integrating between minus p, an odd function, so we have a 0 here. So there is no, so a0 and an are 0 for every n. And finally, for bn, here we are using Euler's formula, and here the new information, f is odd, sine is odd, then we get an even function. And we can use the property that when we are integrating an even function from minus p to p, this is exactly 2 times the integral from 0 to p of the even function. So, in conclusion, for a function 2 periodic odd, the Fourier series representation is given by this guy, which only has signs in the series. And the coefficient bn, we can simplify the computation in this way. It's 2 over p, the integral from 0 to p of f times sine. Okay, let's see an example where we can apply this new technique in some sense. We are still studying Fourier series representation. The only difference that we have here in this part of the lecture is that we introduce this concept of even and odd function, and this makes really easier the computation of the Fourier coefficient when we are working with this type of functions. Okay, so find the Fourier series of the 2 periodic function f 1 minus x squared, where we have this x between minus 1 and 1. Okay, so notice the graph of f on this interval is a parabola, and it repeats itself because it's a periodic function. So we have this guy, this guy, this guy, and so on. Now, if we take a look at this interval and this piece of the graph, we can see that the graph is symmetric with respect to the y-axis. And also we can just check, but by the definition of even function, that this function is an even function. So this is what we are going to do. So we can use the simplification of the Fourier series representation. So once we know the graph, it's really easy to try to guess if the function is even or odd, because we are just we need only to check, okay, is this function symmetric with this with respect to this guy, or is this function symmetric with respect to this guy? Okay, so that's why maybe having the graph of the function is quite useful. So first, from the graph, we suspect that the function is even, and then we say, like, okay, we'll have to verify that because we have to justify what we are saying. So, okay, f of minus x is 1 minus x squared, and again, minus x squared is just x squared, so this is exactly f of x. So we have that f of x is even. Now we use the new representation of Fourier series, the Fourier series representation of f for an even function, and we know that this is the representation. Here p is equal to 1 because f is 2 periodic, and we know that we can compute a0 in this way. Instead of having the minus 1, and 1 over 2 here, we use this new representation of the Fourier coefficients, and we have to integrate this function. And we have an equal to 2 times the integral from 0 to 1 of f times the cosine, and is this. So it remains to compute these coefficients. Okay, so we look for an antiderivative of this guy, which is this guy, and we evaluate in 1 and subtract this number, but evaluating in 0, and finally we get this 2 over 3. For the computation of an, we can use integration by parts, that here is a quick reminder about what integration by part is. So we call a function u, and we call the other function b prime, and we have this identity. And the idea is to, when we get this guy, this new integral, this one should be easier than the original one. Otherwise, it doesn't make any sense to do integration by parts. So doing those computations, that we are not going maybe to spend a lot of time in the computations, but you can you have here the solution. So we call this guy u and this guy b prime, and then we get an antiderivative of this guy and the derivative of u. And you can see that this is simpler than u, because it's just a polynomial but order 1, and this one is order 2. Okay, so evaluating this guy between 0 and between 1 and 0, we get a 0 here. You can check that. And again, this we have to do integration by parts again, because yeah, it's still not yeah, it's the only thing that we can do. Okay, so again, we make some computation and simplifications there. We call again this guy u and b prime, and do integration by parts again with this guy. And here you have the details of the computations, and we find this expression here. And now take a look to this guy, cosine of n pi, and you can see that for n equal to 2, 4, 6, 8, and so on, the value of this guy is 1, and for n equal to 1, 3, 5, 7, cosine of n of pi is -1. So we have a way to write down, to rewrite this guy as -1 to the power n. Okay, so we use this information here, and then notice that the guy that is here is equal to 0. You can compute that. I'm putting all this information together, so going back to the computation of an, what we get is this expression. And this -1 is because we have a minus also here, so we have to take it into account. And we finally get the expression of an. So the Fourier series representation of f is given by 2/3 plus this is an, and this is the function cosine n pi x. Okay, if we want, we can take this as a common factor, 4/pi square, and we can put it in the front of the series, but it's not super necessary. But this is the expression that we get from the Fourier series representation of our even function 1 minus x squared. Okay, some remark. When we have to find the Fourier series representation of a periodic function f, it is useful to check whether f is even, odd, or neither. So if f is even, we will know automatically that there is no bn, meaning that bn is equal to 0 for all n. And if f is odd, we will automatically know that a0 is 0 and an is 0 for every n. So that's why we are spending time in these properties of a function being even or odd, because in those cases we can clearly simplify the computation of the Fourier coefficients. Okay, and that's it for this second part of the lecture.